Hello everyone, welcome back to my channel. So today we're going to go over this problem of control. So basically a block of mass m1 slides on a frictionless track with a box of mass 2 which itself slides along the frictionless ground. A force Ft is applied to the box. A spring connects the block to the box. The coordinate x1 measures the position of the left edge of the block, and m1 and x2 measures the position of the left edge of the box, m2. Assume the spring is stress-free when x1 equals x2 equals 0. Use this figure for problem 11. So find the equations of motion for the mechanical system in figure 5 in terms of the coordinates x1 and x2. So what is happening over here? So it slides on a frictionless track within box of mass 2, which itself slides along the frictionless ground, and force is applied to the box. Spring connects box to the block to the box. Coordinate x1 measures position of left edge of the box of the block. M1 and x2 measure position of left edge of the box. Assume spring is stress-free when x1 equals x2 equals 0. Okay, so for equations of motion, what is happening over here is complicated because each of these are moving relative to each other. So first thing to do is to draw a free body diagram. And we need to draw two, one for the block inside and one for the block outside. So for the block inside, it's going to be a block with weight 1. Let's call it W1. And there'll be a normal force from M2 acting on the block. Let's call it N1 as well. And there's going to be a force, friction force, no, actually, sorry, spring force acting to the left. Let's call it Fs because it's spring force. What about for the outer portion? We know that this block is going to have a weight associated with it, which is going to be weight 2, W2. And there's going to be a normal force acting down on the block from the weight of the first block. And there's going to be a normal force 2 acting up on the block from the ground. And the spring force is yes, by Newton's third law, and every force must have an opposite force associated with it. There's going to be another spring force pointing to the right, since this point over here isn't really moving. This is going to be Fs, and there's going to be Ft, the force exerted on the block. So and why is the weight of the block not accounted for? Well, it is accounted for in terms of the normal force, but basically, normal force and this spring force comes from the force of the first block on this second block. Yes. So now that we have our free body diagram, the next part is to come up with um force balance equations. So the coordinate system associated with it, the coordinate system is x1, x2, and we need to draw a free body diagram, and the force motion relationship is spring. And according to force motion relationship, this motion is according to spring is equal to Fs times k x1 minus x2. Oh wait, so sorry. Actually, I was saying Fs is equal to k times x1 minus x2. And let's take a moment to understand why it is x1 minus x2 and not plus. It's because these two blocks are moving in the same direction, and so uh, it will cause this spring to be more relaxed than if only x1 was present. Because as this spring system, as it's moving to the left, this whole portion where the spring is attached is moving to the right, so it's going to stretch out the spring a little bit and make it more relaxed. Conversely, if these two are pointing in the opposite direction, it's going to be added. The spring force is going to be greater. And basically, we want our sum of forces. So the sum of forces is going to only be in the x direction. So the sum of forces in the x1 direction is going to be sum of forces equals MA. Sorry, and I forgot to include one thing is the negative spring force is actually the one equal to F of S equals Kx minus x2 because so x1 is moving here. Oh, okay. And then yes, the spring force is actually pointing to the left, so it's going to be negative. So F is equal to MA, and this is equal to for the mass one is equal to M1 times x1 double dot because double dot is like differentiating the displacement x1 two times, which is going to be acceleration. And this motion is going to be uh basically pointing in the opposite direction as the spring force. So it's equal to negative Fs. Mm. This is actually going to be equal to negative k x1 minus x2. Yes. So what about for m2 in the x2 direction? Yes, then actually for this one on the left it is actually negative sum of forces equals MA. And also for the x2 direction it is negative sum of forces equals MA, and this is equal to M2x2 double dot. And it's equal to, let me see, there is the force Fs pointing to the right and Ft pointing to the right as well. So this is equal to Fs plus F. And Fs, as we saw earlier, is k kx1 minus x2. So f of s is equal to that, and we have this is equal to k x1 minus x2 plus f. And from here we can and here we have gotten the equations of motion for the mechanical system in terms of the coordinates x1 and x2. So, Okay, I was wondering why the sum of forces is actually negative. And that is because in the equations of motion in this problem, it's related to the way the spring force is defined and applied to the masses. So the spring force definition is Fs equals K x1 minus x2, and it's defined as positive when the block M1 is to the right of the box M2. The force tends to restore the spring to its natural length, so it acts in opposite directions on the two masses. So for M1, the spring pulls the block to the left if x1 is greater than x2 because the spring is stretched. So the force on M1 is to the left, which is the negative direction of x1. So the spring force on M1 is negative Fs equals negative K times x1 minus x2. For M2, the spring pulls the box to the right if the block is to the right, so the force on M1 is to the right, which is the positive direction of x2. So the spring force on M2 is Fs is equal to K times x1 minus x2. The sum of forces for each mass includes the spring force, but with opposite signs for each mass because the spring pulls the two masses towards each other. For M1, the spring force acts in the negative x direction, so it appears as negative Fs. And for M2, the spring force acts in the positive x direction, so it appears as positive Fs. This explains why the sum of forces involves a negative sign in one equation and a positive sign in the other when applying Newton's second law. Yes. Yeah, so these two are our equations of motion over here in terms of acceleration. And I hope this video was helpful for you guys and see you guys in the next video. I'm gonna be posting these slides afterwards as well. Thank you guys again for watching.